This video is part of a playlist on quantum mechanics. You can find the link to the playlist in the description below. In this video, I want to talk about the Bohr radius. In a previous video, we actually derived this expression for the radius. So this is the radius of a circular orbit associated with an electron in the Bohr atom. So we kind of generalize this not just to hydrogen, but to other hydrogenic or hydrogen-like atoms, like lithium as well. So these other elements can also be described by Bohr's model. And that is what this general form is actually saying. That's why we've included this capital Z, which is the atomic number. For hydrogen, this is actually going to be 1, which we'll see in a second. So this expression over here, which we derived in a previous video, is in terms of n and a bunch of other constants. So h bar, that's a fundamental constant in quantum mechanics. It's a very, very important constant that keeps showing up all over the place. K, that's Coulomb's constant, which we can also write as 1 over 4 pi epsilon naught. And other versions of this formula actually repackage this K upstairs, right? You can actually see a 4 pi epsilon naught up here instead of just a K. But this is a more condensed notation. E is the charge of the electron, and it's actually squared, so we don't care about the sign. But the electron has a negative charge, and the protons in the nucleus, they have a positive charge. This M over here is referring to the mass of the electron. So these guys are all clearly stated in the derivation in the previous video, where we derive an expression for the radius for the Bohr model. So what can we see in this expression? Everybody is a constant except n. So we can group all of these guys together into one constant. We can call that R1. That is the radius associated with n equals 1, or the first radius. So the first radius we can call R1. Then what we can do is we can just move this n squared out over here, and we can write any possible radius in terms of the first radius. So the first radius is going to be n equals 1. The second radius is going to be n equals 2. And that's actually going to be 2 squared times R1, which is 4 times bigger. And we can continue like this. The third radius is going to be 9 times bigger, and the fourth radius is going to be 16 times bigger. So it grows with a square. It's a quadratic proportionality. So that's an important observation to make. Now let's switch over to hydrogen. So far we've kept it general. We've kept it general to any element that behaves in a similar way to hydrogen, in that it has a bunch of protons in the nucleus and it has one electron zipping around in a circular orbit. So what can we do to set apart hydrogen and make hydrogen the special one? Well, we can actually set this capital Z, the atomic number, equal to 1. So let's go ahead and do that. If we set Z equal to 1 for hydrogen, then what happens to this expression over here? Well, this Z can just be treated as a 1, so we can ignore it. It's just multiplying by 1. Then what we can do is we can write this in terms of A sub 0, or A naught. And this denotes the Bohr radius. So the Bohr radius takes the place of R1. Or R1 is actually the Bohr radius if Z is equal to 1. So this expression over here is the expression for the Bohr radius. And we can see that it's around half an angstrom, which is 10 to the minus 10 meters. And half an angstrom corresponds to around 5 times 10 to the minus 11 meters. So this is a very small distance. And it actually corresponds to the most probable distance the electron will be from the nucleus. So we haven't actually derived that yet, but what we have derived is an expression for this radius. But we don't know why it is the most probable radius. It turns out that it is the most probable radius, and we'll see that when we solve the Schrödinger equation. So the important message of this video is that we've actually derived this expression, which generally works for any atom that behaves like hydrogen, and then we've set Z, the atomic number, equal to 1, and we've got an expression for the Bohr radius, or A naught. And this is the actual numerical value, or a decent approximation to 3 significant figures. So if you're looking at other resources, you might see slight different variations on the expression of this expression over here, So you might actually see different constants appearing. And why is that the case? Well, it's because k can be repackaged. You can actually write these in terms of different constants, and you will still get the same answer. So make sure you watch the rest of the videos in this playlist to get a more complete understanding of quantum mechanics. You can find a link right over here.